Hey guys, so we're going to be trying out what I want to call a hybrid tutorial. That name is subject to change, but it's what we have right now. And essentially, this is number -1. I don't know why I'm counting from negatives, I just kind of want to. And this is essentially going to be both a video component and a blog component with text, which is kind of already written in one. Now, the two I kind of describe more inside the blog itself, but the two are designed to supplement each other. So you can still learn the topic without necessarily watching the video and reading the blog. However, it's generally beneficial to have both. They're going to be in sync, kind of, as in they'll go through the same flow, same structure, and yeah, hopefully it should suit everyone. As in, people who prefer blogs and people who prefer videos can both be happy. So, heavy light decomposition. That is our topic today. It is very cool what it does. So, let's start with the problem. Let's say you have just some array. Say it just wouldn't be a right video if you don't have awkward usage of paint. So let's say you have just an array. I don't know, some elements, right? And so you have two types of things you can do. You can ask for the XOR, I'm not going to use yellow. You can ask for the XOR of a contiguous range of the array, for example, from L to R. In this case, it's 7 XOR 5 XOR 4, which is 1, 1, 1, 1, 0, 1, 0, 0, 1, and it comes out to 6. So the answer for this would be, the answer for this query would be 7 XOR 5 XOR 4, which is 6. And the other type of thing you can do is you can change one type of element to another, or you can pick one index and you can change the element at that index to a different one. So I'll change the 7 to a 6. And then now, when we ask for further queries, this will have that change. So we'll ask for 3 XOR 6 XOR 5 instead of 7. So this is a very basic application of a segment tree, where you can just ask for XOR range queries and essentially point updates. So this is too simple. What we're going to instead do is we're going to put this problem on a tree. And I'm just going to copy the tree from the blog to be consistent. Paste that in and then use it. And then, yeah, it's the same color scheme. Cool. So now we will ask for the same thing. We're going to give each vertex a value. Let's say this is 7, this is 6, this is 5. It doesn't really matter what the values are. And we're going to say change a vertex, or yeah, so the possible queries are change a vertex, or query the full XOR of a path. And a path meaning the path between two vertices. For example, if I select the path between these two, it would be these. And these would be the vertices we'd be interested in, because it's a path from this vertex to this one. And the other type is just you change the value of a vertex. So, with my terrible handwriting, this is harder. Like, you can't build a segment tree on a tree because it's not a straight line anymore. This is a specific problem that I'll be linking in the blog, so you can try that out once you finish this. And yeah, so before I get into, I will get rid of this. Before I get into how we actually do this, I'm just going to add some prerequisites first, because this is kind of an advanced topic, so there are some things you should know. There's some things you should know before trying this, and they're essentially trees, like what a tree is, like what this thing is, and how to traverse a tree. And specifically DFS, because that's what my implementation uses, and it's a very simple way to work with trees. You should know segment trees, because they're kind of the whole point of heavy light decomposition is to be able to use a segment tree. Segment trees. Sorry, I'm still using my mouse for this. You should know binary lifting, because my implementation uses it, and it's also generally a good thing to know. Basically, binary lifting will let you, like say I'm here and I want to get the third ancestor, I can do that in O of log n time. Kth ancestor. So that's what binary lifting will do, and it's very useful. You'll see how it becomes useful in this implementation, kind of. And another thing is the LCA, or lowest common ancestor of two vertices. And if you already know binary lifting, this one is easy, because you can use binary lifting to get LCA in O of log n. So the LCA of two vertices is the lowest vertex as an ancestor of both of them. So for these two, it would be the root, because this vertex is the only ancestor of both of them. For these two, it would be this vertex, because it's the lowest that's an ancestor of both of them. There's also the root, which is an ancestor of both of them, but it's not the lowest. So that's why we picked this one. So yeah, those are the prerequisites. You should know those before watching these. Okay, so now we'll get into what we're actually doing. So what we want to do is essentially we want to turn this tree into something that we can use a segment tree on. And unfortunately, we can't directly do that. There are ways we can flatten a tree, but it won't allow us to support queries on, let's say, paths. So there's something else we can do. What we're going to do here is we're going to look at each vertex, and we're going to say, for this vertex, of all of its children, we're going to identify the child that has the largest subtree. So I'm going to mark out the subtree sizes right now. This has a size of 1. This has a size of 2. This has a size of 3. 1, 1, 3. We're including the vertex itself. 1, 1, 1, 4, 1, 6, 3, and this is 13. So then what we're going to do is, once we identify this vertex, we're going to call it essentially the heavy child, and we're going to mark the edge that goes to this child as a heavy edge. So this edge, actually we can use flood fill here, I think. So this edge is heavy. That looks terrible. For this vertex, this edge is heavy. And we can essentially pick arbitrarily when there's a tie, it doesn't really matter. For this vertex, we'll choose this one. And for this vertex, this is the only edge to its child, so it's the heaviest, and same thing here. So now we have these poorly colored in green edges, which signify that they're heavy. And now there are multiple cool properties about these heavy edges. The first being that these heavy edges will always form vertical chains. What that means is it's a path from some vertex up to an ancestor of it. It won't ever go back down the tree once it starts going up. And you'll see later why these are very nice to work with, because we're going to be using more vertical chains, and this is a nice representation. So another thing about this is that not only do these form vertical chains, but there's this very cool property, kind of the whole point of heavy light decomposition, that we can use. And it's that any path on the tree, let's say I'll just draw any arbitrary path at all. Any path, write this out too. Any path goes, actually I'll uncircle that path first. Any path goes through at most O of log n light edges. Now this is kind of a big claim, because say this is true, then what we can do is, the point of the implementation is that we'll build a segment tree on each of these vertical chains that we have from essentially the chains of heavy edges. So we'll build a segment tree on, for example, these three, and this one, and these two. So we'll have 3 segment trees in total, or one big one depending on the implementation. But the point is we have a segment tree on these heavy edges. So because it visits O of log n light edges, it also only visits O of log n chains. So if we can evaluate the value at a light edge or a light vertex in O of 1, and we can evaluate the value of a heavy chain in O of log n because we have segment trees on them. So that means the total time to evaluate a path is O of n times log squared of n. Because we have O of log n, or wait, sorry, this should be just O of log squared of n. That's ugly. It's bothering me. O of log squared of n, sorry. And this because we have O of log n light edges and also O of log n heavy edges, and therefore it takes O of log n queries to the segment tree, each of which take O of log n time. So it's O of log n times log n. Alright, now this is a very big claim. How can we in fact prove that a path goes through at most O of log n light edges? Let's just do it out. So here's the proof. Let's say we're at a light vertex. I'm going to use the same color scheme, that red is a light edge and green is a heavy edge. So we have, and we're going to prove that we go through at most O of log n light edges. And it's clear that if we go through O of log n light edges, at the same time, we'll go through O of log n heavy chains, because a heavy chain will only be broken by a light edge. So let's say we're at this vertex. There are only 2 cases for when we go up to a parent. That either we go up a heavy edge or we go up a light edge. And there's also something important to mention, something that makes this representation very easy to work with. Any path through the tree, any path through any tree can be broken up into 2 components. Let's say we have this vertex and this vertex. it can be broken up into the path from one vertex to the LCA, the lowest common ancestor, and then the path from that LCA down to the other vertex. Which means we can break each path into at most 2 different vertical chains, just like these light edges are, just like the heavy edges form vertical chains. And the reason this is true is because what we're claiming with this is that every path goes up and then down, and it might not go up or it might not go down. And it wouldn't be possible for a path to say go up and then down and then back up again, because if we did, then look at this vertex. It has 2 parents essentially, one that it comes down from, one that it goes up to, or one that goes down to it and one that it goes up to. But in our representation of a tree, we can't have that. That's just not how we represent trees. So essentially we can't have it go down and then back up. So when we're at here, we can start going up to the LCA, and then once we go down, we always go down and we can never go back up again. So there are only 2 vertical chains in each path. So now once we do that, we just have to prove that each individual vertical chain only goes through at most O of log n light edges. And that is slightly easier to do. So there are 2 cases where we're going from a vertex to its parent. Use a different color. Either we have a light edge or a heavy edge. So we're proving that we go through at most O of log n light edges. So we don't really care when we have a heavy edge. We only care what happens when we have a light edge. So let's see what happens. If we have a light edge, that means that this vertex has another child. And this other child has a subtree size that's greater than or equal to this subtree size. So I'll use notation here. This is vertex A that we're coming from. This is the parent P, and this is vertex B. So size of B is greater than or equal to size of A, because otherwise A would be the heavy child. So therefore, size of P is, well, it's a parent of both of these, so it has to be greater than size of B plus size of A. Don't know why I put a parenthesis there. Then, but because size of B is greater than or equal to size A, we can say that size of P is greater than or equal to 2 times size of A. Now this is good, because what we can say now is that because the size of the parent is greater than, doesn't even matter if it's greater than or equal to, it's greater than 2 times the size of A, what we can conclude from all this is that when we have a light edge, the size of the subtree that we're at least doubles. So we can only double at most, let's say, log base 2 of n doubles. Because otherwise we would exceed n. We can't have a subtree size that exceeds n. So therefore, we'll only double at most log n times, so we'll only go through at most O of log n light edges. And that's essentially the proof. So this is, what did I just do? This is the main concept of heavy light decomposition, that every path will go through at most O of log n light edges. So the total time to evaluate a path, if we have a segment tree on these chains of heavy edges, is O of log squared n. So now essentially we have the concept. But the implementation is also a bit tricky, because how do we just build a segment tree on these heavy edges? Well, there are certain tricks you can do, like smart different types of DFSs, and I will just go over the way I implemented this, since I feel like it's relatively straightforward once you understand everything. So first, we begin by finding the heavy edges, and well, we've kind of already gone over how to do that. We find the size of the subtree of each node, and the way we do that is size of a vertex v is equal to 1 because we count v, like 1 because it's the vertex itself, plus the sum over u, as in u is an element of the set of children of v, which essentially means that we just sum over all of the children. Size u. Sorry, this should be u is an element of child v. So now, let me illustrate just doing that for this vertex right here. So this vertex contributes, or I'll do it for this vertex. So this vertex contributes 1, this child contributes 1, and this child contributes 4. So the total is 1 plus 4 plus 1, which is 6. That's how we do subtree sizes. Then we simply look at all the children and we just see which one has the biggest subtree. That's how we get heavy edges. So we're also here, we're going to store depths because it's going to be useful later. So right now I'm going to mark the depth of each vertex, which is the distance from the root. And this is 1, this is 1, this is 2, this is, I'll mark that here, this is 2. Very struggling here with the drawings. This is 2, this is 2, and these are all 3. Okay, so now we have to find these heavy chains. And what we want to do is, we want to find, essentially for each vertex, the top of the chain it belongs to. That way, once we'll say here, and our path is going up here, we can just jump to the top of the chain without having to do any work, essentially. Now we computed subtree sizes with essentially a bottom-up dynamic programming, where we just say any leaf is 1, then we sum over the size of the children, then we just do that all the way up. And this time we're going to do it with a top-down version of dynamic programming. So let's say initially we start here. So the top of the chain of the root is 0. Then we'll, I guess, go down here. So now the top of this chain is 1. And because this is a light edge, alright, actually, what I'm going to do first is I'm going to give these nodes all of their labels. And we're going to label the nodes such that, well, we want to label them so we can build a segment tree on top of them. So we're going to label it such that every heavy chain forms a consecutive sequence of numbers. And the only way we have to do that is we start here with a 0 at the root, and then all we have to do is visit the heavy child first. And that way you can see that these are going to form consecutive numbers along this heavy chain. Then we'll just continue in the DFS, go back up here, go down here, label these arbitrarily, and then we'll label this with a 5. Go back up here, label this arbitrarily with a 6. Go back up to the root. Now we label the rest of these arbitrarily. So this is 7, this is 8, this is 9. We go back up to the root down here. This is 10. We visit the heavy chunk first. This is 11, and this is 12. So now we have the labels, and brown is a label. I should keep a legend of these. So brown is label. Purple is size. And orange is depth. So now we're going to compute the top of each heavy chain. Like, for example, this vertex, the top of its chain is up here. For this vertex, the top of its chain is up here. And this vertex isn't on any chain, so its top is itself, essentially, because there's no heavy chain that leads above it. So we'll start by labeling the root with 0. Then we'll go down to any vertex, and we'll label this with 1. And because there's a light edge above it, we'll label this with 1 because it's label 1. Essentially, we're going to label it with itself first. How did this end up here? I don't know how I had a 0 there. Okay. So we're going to label this with 1. However, because this has a heavy edge leading above it, it leads to the vertex 0. So we're going to set this to... We're going to set this essentially to the chain of its parent. Then we'll go down here. Alright, sorry. This should be a 0 because its parent is 0. Then we'll go down here. Now we'll initially set this to 2. However, it is a heavy vertex. So we'll set it also to the top of the chain of its parent, which is 0. And we'll do the same thing here. This is a heavy vertex, so we'll set it to 0. Now this is not a heavy vertex, so the top of its chain is itself, which is 4. Same for here. Same for here. Then we'll go over here. This is a light vertex, so the top of its chain is itself. This is a heavy vertex, so the top of its chain is the top of its parent's chain, which is 7. Same for here, heavy vertex. And then this is another light vertex, so we'll set this to 10. This is a heavy vertex, so we set it to its parent's value, which is also 10. Then this is a light vertex, so it's itself. And these are how we create the tops of the chains. And now we have an absolutely massive mess of numbers. So this is, if you've ever seen a heavy light decomposition implementation, there are always tons of different arrays that you have to store because there's so much information you need to do this. So this is all the pre-computation we did. You don't really need to focus on these numbers. They're not that important. We'll just use them. All right, so now we get to the fun part. So queries and updates are basically the same thing as long as you have a lazy segment tree, because both of them will assume updates are on paths, and then if you're updating a single vertex, it's just the path from this vertex, for example, to this vertex. So you can just update it like that, and same thing for individual vertex queries. Now, we're going to use the same thing, essentially. We will say that any path, let me find a color that I haven't used yet. Does this work? Yeah. So any path from any vertex to another vertex can be broken up into two parts. The path from the first vertex to the LCA, and the path from the second vertex, or the path from the LCA down to the second vertex. So in the implementation specifically, we can compute this vertical chain, and this vertical chain, and then we'll include the LCA in our answer. So we compute the vertical chains excluding the LCA. Now, what we need to do here is we need to figure out how to compute a vertical chain. And this is the most fun part of all. So we see how we have these numbers. However, most of them, we need them for the implementation. However, I'm going to take a different example here. We're going to say, using the same notation of green, I'll draw out a bunch of vertices. And I'll also write out that our answer is chain 1 XOR chain 2 XOR LCA. And that's what we do. So now all we need to do is compute a chain. Let's do that. So we have, draw one more vertex. And actually, wait, there's a better, yeah, we'll do this, and then that, and then that. So now we're going to say we're going to compute this chain and exclude this one. So first, we're here. This is a light vertex. So we can simply take the value of this vertex. Then we take the value of this vertex, we XOR it with our answer, then we move up to its parent. And then, now there's a way you can combine these in the implementation to treat heavy and light vertices the same. That's why I set, for light vertices, I set the top to themselves. So you'll essentially compute the segment tree and you'll query only the light vertex. And then you'll move to the parent of wherever the top of the chain is. In this case, it's itself, so you move to this parent here. So now that's clear in the implementation basically. So this will be here. And now we're going to move up. Well, since this whole chain is contained within what we're querying, we can essentially query the whole chain and then move up to here by using this. Actually, we'll query the whole chain, all three of these vertices, and then we'll move up to the parent of the top of the chain because we've already included this vertex. So we can do that with a single segment tree query since we already have all of this. So now we're here, and yeah, so we kind of just ignored this whole light edge because we can jump from here and use a segment tree query. So now we're here, and the issue is the top of this chain is not included in the path. So what we need to do is we need to find this vertex. And there are many ways you can do this. You can, for example, we know that all of these labels are consecutive, so you can take the difference in depths between, let's say, this one and this one. We know that these are one depth apart, so we can jump one depth up in terms of labels. Similarly, we can also use, I don't know why I did this in my implementation, but it doesn't really add that big of a, it's not that big of an effect on the constant factor, but you can use binary lifting to find the, essentially the, this is 2 minus 1, so the ancestor, the kth ancestor of this vertex, such that it's right below this one. There are many ways you can find this exact vertex. but all you need to do is find it. Then we will query the segment tree for this vertex to this vertex, and then we will essentially return the answer because we're done. We've hit the top, and there's no reason for us to keep looking at this vertical chain. And so let's say this was a light edge, then it would be even simpler because we wouldn't have to worry about the chain at all. We would go directly up here and we'd say the top of this chain is higher, so we'll just take this vertex and then stop. So either way, the implementation handles both, and we're going to grab exactly this region by making sure we don't overshoot by going up in the chains. So now we've computed both vertical chains. So we can compute chain 1 and chain 2, and the value of the LCA is just the value of the LCA, so it's simple. And therefore, we can just include that. So both chains are O of log squared n, log squared of n. The LCA is whatever, it's just a segment tree query, so it doesn't matter. So in total, this whole thing is again O of log squared n per query. Okay, so there are more details that I gave in the blog for the exact implementation. It's just kind of a list of stuff to do, so I'm not really going to list it out here, except there's one more thing I should talk about, and that's how to make this work for edges, because this works for values in vertices. In the problem, we want to compute the XOR of vertices on the path. But what if instead we have weighted edges, for example, and we want to do the same thing for an edge problem? It's actually very simple, because in a tree, every vertex except for the root has a parent. Notice here how the root is the only one that doesn't have a parent. Everything else has something above it. So similarly, every vertex except for the root has an edge that goes up from it to its parent. So we can use the vertices themselves to represent the edges that go to their parent. For example, if this edge had value 5, then we would just shift it down to this vertex and say this vertex has value 5. Then we have to change virtually nothing about the implementation. All you have to do is make sure the labeling of the vertices is right so that each vertex gets the appropriate edge's value. I know that many templates have a use edges Boolean flag, and it basically does this. Mine doesn't because it would be, I think, slightly complicated to do that, but it's a good exercise to try and modify this so that it will also work with edge queries. Anyway, that's essentially it. You compute to make heavy light decomposition work. You have to prove this, then the total time is O of log squared n. Then you compute all of this information about the tree, and then you get your answer as the combination of two different vertical chains combined with the LCA. And if you're using the thing for edges, then say, for example, you want, still not using yellow, then say, for example, you want this path, then you would include this vertex, this vertex, this vertex, this vertex, this vertex, and this vertex. But you wouldn't include the LCA. So for edges, the answer actually doesn't include the LCA. It would just be the two vertical chains. That's another thing to look out for when using edge updates, or edge queries. So in general, that's it. The blog basically goes the same route. So, yeah. So you can, again, use the blog and the video to kind of supplement each other. If you don't understand one part in the video, you can also check out the blog, because they're basically going over the same things. Yeah, that should be it. Thank you for watching.